Alright guys, welcome back. Hopefully today will go as quickly as the last video. I am doing this outside today. This is me outside in my backyard because I am tired of being inside and sitting. So, doing this outside. Hopefully you can as well, unless you're doing this at midnight, which then I would not recommend. So the last set of this 5-1 notes, they're going to go pretty quickly too, and then we're just going to practice tomorrow. I am in grade, probably 2 of the questions just to make sure you're paying attention, but otherwise you should be good to go. So we are going to get started. So this is asking us for relative extrema. Just a reminder that what that means is max and min points. Max and min. If you forget how to find relative extrema, I will refresh your memory. So, relative extrema. Just a reminder that the relative extrema, your derivative is going to equal 0. So, I know it's kind of weird for us to go back to derivatives, but hopefully it feels like a nice little change, a little back into what we used to do. So, our derivative here would be 1 minus 1 over x, okay? To figure out where we have our extrema, you set that equal to 0. And then solve. So I would personally subtract the 1 or add the 1 over x. Adding 1 over x will get a positive value, which is nice. And then cross multiply. So x times 1 equals 1. Okay? So just a reminder that when you have an exponential function or an exponential rational function like this, 0 can't be in your domain, which is important when making your number line to test whether this is a max or min, okay? So, we want to set up our number line to check whether something that we're solving for is a max or a min. So what we can do is off to the side, set up our number line. This is for f prime of x. So we actually want to use 0 and 1. If you think back to rational functions when we did it in pre-calc, there could be an asymptote there, which is why it's important to check both. So basically, whenever you have a rational like that, you want to use 0 as well, even though you don't solve for 0. Okay, so what we want to do is test points on either side. So plug in a number to the left of 0, in between 0 and 1, and to the right of 1. So I would do like f prime of negative 1, f prime of 1/2, and then f prime of 2. So take a second, plug in some numbers for our derivative, and then include your number line. So you want to do the plus, minuses, whatever you get. Pause the video, and you should have what I have when you're done. All right, so hopefully you got plus, minus, plus, which means that at 0 you are increasing and then decreasing. So technically that would be a maximum, but we know that that's an asymptote, if you remember from, again, rational functions. So we actually want to make sure we're just looking at the 1 here. Excuse me. This is decreasing and then increasing, so that means 1 comma something is a relative min, okay? And to find out what that something is, you can plug in the 1 for your original equation. So I would literally do 1 minus ln of 1. If you figure out what ln of 1 is, it's 0, so this is 1 comma 1, okay? The reason you can't test the 0 point is because if you try to plug that back in for the value, you get 0 minus the ln of 0, which is 1, which is negative 1, and you shouldn't have that as a point on your original graph, so that's your relative min only, okay? Your possible points of inflection are when your second derivative is 0. So you want to take your second derivative, the derivative of your derivative, so you get 0. If you forgot how to take the derivative of 1 over x, change it to x to the negative 1. So feel free to turn that into your what? There's a bug. Sorry. Bug just flew onto me. Yikes. Benefits of being outside. Sorry. Anyway, you get, this is the same thing as 1 minus x to the negative 1. So if you take the derivative, it's 0. And then plus x to the negative 2, which is the same thing as 1 over x squared. Okay? So if you set that equal to 0, you get 1 over x squared equals 0. So you actually end up with, remember, it's where you're looking for where your derivative and your second derivative are 0 or undefined. So where this is actually undefined is at x squared equals 0, which is x equals 0. So when you check that, you have to put it on your number line, right? You plug in 0. The only problem is if you look at the domain of this function, if you look at x squared, the negatives, 1 over x squared, the negatives actually don't exist for y values. So if you try to plug in like negative 1 into your second derivative, you get 1 minus 1 over 1, so you actually get like negative values here. So you can't do that. But if you plug in numbers to the right, we unfortunately cannot tell anything about this because we can't plug in values to the left. 0 is not in our domain for this, so there is no point of inflection. We can only plug in points to the right, which doesn't even tell us anything. Because remember, a point of inflection would be if you have no change in between your number line values. For some of us, it might actually help to graph. If you actually plug in x minus ln of x into your graphing calculator, you'll notice that negative values are not possible. But you can also think back to, like, the reason why we can't plug in for these negative values is because in the original function, the x minus ln of x function, you can't take the ln of negative numbers. So if you tried to plug in for those, you actually can't make that happen. You can also verify your answers by the graph too, because the only min is at 1, 1. So hopefully that'll help you to see a little bit better. All right, so for the second one, I'm going to have you actually try this one out. Locate your relative extrema and points of inflection. Just a reminder that your extrema are where your derivative is 0 or undefined. So you'll have to think about that one. In this, feel free to use some of those properties of logs if you want to before you take the derivative. But just a reminder, either way, you're going to have to use the product rule. So just be careful of that. Okay, so try it out, and I'll have it done for you in a sec. All right, guys, hopefully you got to this point. If you didn't use the properties, you probably get the same answer from what I have. In this, I factored a lot, so I factored out an x here. Just a reminder, you can't take the natural log of 0. That's another reason why in the last problem, even though we get 0, you can't actually plug it in, because you can't say that anything raised to a power will give you 0 back, so that's the tricky part. So we actually get, if you plug this in, if you add the ln of 4, subtract 1, divide by 2, you get something that looks like ln of x equals, I actually might subtract the 1 first, ln of plus ln of 4 over 2. That's just a number. If you plug that into your calculator, and then you can put it in exponential form. So you could say e to the power of this equals x. So you end up with x equals 2.43 as your answer. So that is what you want to put on your number line. Okay, so 2.43. Again, to figure out whether it's a max or a min, you plug it into y prime, the numbers to the left and the right. So I'd plug in like 1. Just be careful you can't go into negatives here. it's helpful just to recognize that either by the graph or by looking at log functions. If you remember the basic log graphs, the domain is always from 0 to infinity, so you can't plug in negatives here. So plug in like 1 or 2 and then maybe 3. And what you end up with is a negative and then a positive. So that means that would be a minimum. So our min, relative min, is going to be at 2.43, comma, whatever I get after I plug that into my original, right? So you end up with about negative 2.94 is what I got. Okay. All right, the last one on this page is just finding we already found the extrema, okay? Notice this is the same question, so now you can just find the points of inflection, so you have a little bit more room. So my possible points of inflection, I need to find my second derivative. So if you didn't find the same derivative I had, just a reminder that your first derivative was... I got x times, some of you may have had 1 plus 2 ln of x over 4 if you used just the product rule. But I get, if I did this out, my first derivative was x times 1 plus 2 ln of x minus ln of 4. So again, the other version of that, if you just used the product rule from the previous question, is the same thing as 1 plus 2 ln of x over 4. That's also the derivative. It's the same thing. Just a reminder. You can also get that by condensing this back if you need to. Okay. So now we need the second derivative, right? That's our possible points of inflection. So if I take my second derivative, again, you can either find the product rule, or if you want to just distribute back through, you're welcome to do that instead. So if you want to treat this as x plus 2x ln of x over 4, this is a little easier to absorb, I think, this form of the derivative. So now if I take the derivative of that, the derivative of x is just 1, which is nice, plus, then I have to use the product rule for this, so just be careful. So you end up with 2 plus 2 ln of x over 4. So then, if you do the solution of that, you want to set it equal to 0, right? And if you didn't get that, just a reminder that the derivative of x was just 1, so that's out, right? Then product rule, it would be first, which would be 2x times the derivative of this. Remember, the derivative of that comes out to 1 over x, so it simplifies to 2. Just as a heads up, I skipped some steps there, so if you were confused for a second, that's what it should be. And then second times the derivative of the first, which is, again, 2 ln of x over 4. Okay, so let's solve. So what I would probably do is combine like terms. This gives us 3 plus 2 ln of x over 4 equals 0. So 2 ln of x over 4 equals negative 3 divided by 2. And then I would put it in exponential form. It's a lot easier to deal with. So that ends up being e to the negative 3 over 2 equals x over 4. And then you can just cross multiply. So multiply both sides by 4. You end up with, actually let's leave it in that format. Just so you know, it ends up being 4 times e, which is the same thing as like 4 over e to the negative 3 over 2, 4 over e to the 3 over 2, sorry, if you want to make it positive, which is about 0.89 if you plugged it into your calc. But I'm going to leave it as 4e to the negative 3 over 2. It's helpful to know what decimal it is, though, so you can know what you're plugging in. Remember, we're plugging this in for the second derivative, and it goes negative and positive. So our point of inflection ends up being, because remember, if you forget what that means, like why this is a point of inflection, we're going from concave down to concave up. So it changes concavity at that point. It's just a reminder. So our point of inflection ends up being, you can either do it as 4 over e to the 3 over 2, comma negative 24 over e to the third if you wanted to make it exact. That's if you plug it back into the original equation again. Or what most of us are probably going to want to do is you get 0.89 comma negative 1.19 as an answer. Okay. All right. Second to last situation here is implicit differentiation using logs. So again, probably feels super familiar. However, now we're doing it with logs, so you're going to have to be careful. Okay, so when we do this, we're going to have to take the derivative of each of these. But remember, if you take the derivative of y, it's dy dx. Okay, so if we take the derivative of ln of xy, 1 over xy times the derivative of xy, which means you have to use the product rule. First times the derivative of the second is dy dx, plus the second times the derivative of the first, which is 1, plus the derivative of 5x, which is 5, equals, what's the derivative of 30? That's right, it's 0. All right, so then you can simplify a little bit. Let's cancel some stuff out. So if you distribute 1 over xy through, hopefully you can see that like the x is going to cancel here, the y is going to cancel there. So you end up with 1 over y dy dx plus 1 over x plus 5 equals 0. Okay. So from that point, you can just move everything over, get the dy dx by itself, right? So you can subtract the 5, subtract the 1 over x, you get 1 over y dy dx equals negative 5 minus 1 over x. And then you can multiply through by, you can either multiply through by xy at the beginning, or you can wait until this point. So if I multiply through by y, you have to make this a little bit cleaner. Minus y over x. If you get a common denominator, it'll make this much nicer, which means I can multiply this by x over x. So dy dx equals negative 5xy or yx minus y all over x. That is the nicer version of this. All right, next one, I just want you to use implicit differentiation. I'll help you with the last part where you have to plug in the point. But for now, take the derivative using implicit differentiation, and then I'll show you how to plug in the point if you forget to find the tangent line. See the animal moving around?
What is that?
I don't know. It's been doing that for like an hour. It's probably like a squirrel or a bunny. It was even doing it while I was walking around.
Should we kill it?
No. I don't know. Maybe. We gotta get rid of the moles at some point.
How many mice we've caught?
You wonder how many mice we've caught? I don't know. Okay. So this looks weird. However, what's nice is after this point, you don't actually have that much to do, because what you can do is turn this back into multiply both sides by y, because now we have too many variables going on. So I can just throw a y over here, which I know is weird for us, but then y prime would equal y, or you could say 1/2 y times 1 over x minus 1 plus 1 over x minus 2 plus 1 over x minus 3. I'm not going to make you get a common denominator here, but I am going to have you plug in so we don't have too many variables going on. Because I know what y equals. It's literally this entire expression. So your last step is literally just to plug it back in. So y prime equals 1/2 square root of x minus 1, x minus 2, x minus 3 times parentheses all this stuff okay. So that's your final answer. It looks terrible, but it works. So I'm going to have you try the next one. Just a reminder that you do not want to have to use the quotient rule here, so use some log properties. So try it out. I'll have the work done for you in a sec. Okay, guys, check your answer for me. So remember, you have to take the natural log of both sides when you have something like this, because otherwise it's going to get terrible. And then you can use the properties. So you can separate those into subtraction, so it's easier to calculate. Just be careful that your derivative for these would be 1 over them and then times 2x. What you might see is that I canceled out the 2 from the 1/2 in front because they both had a 2 in it. So you can factor out the 2 and cancel it, and then remember to plug back in for y. So my step from here to here was I multiplied both sides by y, and then this would be your final answer. All right, folks, hopefully it is sunny at some point while you're watching this so you can enjoy some time outside a little bit. Just a reminder that we are going to do a little practice tomorrow with a small assessment thrown in there, so I'll probably grade 2 of them for accuracy, just 2 that are very fair that you've seen, and hopefully you feel good going forward with that. If I don't see you, or if you have no questions or whatever, I hope you have a wonderful, restful break. Obviously, there's nothing to do. I am going to give you a little bit of info about what's happening after vacation, probably posted at some point during next week. So just keep an eye out for how things are going to change a little bit for our class and for other classes, and how grades are going to change a little. So you probably already saw the message from Mr. Petrina, but let me know if you have any clarifying questions as well. All right, have a good one, guys. Enjoy and relax.